when we're describing the kinetic rate of a reaction, we have to account for the concentration of the reactants involved, because the higher the concentration of the reactants you have, the higher probability of collision you have, and therefore the reaction rate will be higher. As the concentration of the reactants drops down, you're going to have a slower rate of reaction because there's a lower concentration of reactant, and you will have lower probability of collision. So when we're writing rate laws, we essentially say that the rate of a reaction is going to be equal to some constant times the concentration of your product of the concentration of your reactants, with each reactant raised to some power. Now that power can't be determined by just looking at the balanced chemical equation like we could with equilibrium. When we're looking at writing equilibrium expressions, we use the coefficient as the exponents in the expression. Here, however, we have to derive them from experimental data. So what we're going to do is we're going to hold one of these concentrations constant through different experiments and look at the impact of changing the concentration of the other one and on the rate of the reaction. So if we're looking to find the impact of changing the concentration of reactant A, what we can do is we can look at the first two experiments because the concentration of B is held constant. When we do that, we see that when we double the concentration of A, the reaction rate doubles with it. So that implies a first order reaction. So if we tripled it and the rate tripled, or we quadrupled it and the rate quadrupled, those would all be examples of first order reactions. So if the impact of changing the concentration is equal to the impact of the change in the rate, that is a first order. If we change the concentration and it has zero impact on the rate, we would say that that is zero order. And if there was a squared effect, for example, if you doubled the concentration and the rate quadrupled, then you would have a second order reaction. Or if you tripled the concentration and your rate increased by a factor of 9, that would also be an example of a second order reaction. So for the first one, for reactant A, we said when we doubled the concentration, holding B constant, our rate doubled. So we would say that this is first order with respect to reactant A. Now looking at the impact of B, we could look at the first and the third experiment because A is held constant and we double the rate of B. And we see that when we double the concentration of B, when we double it, it has no impact on the rate. So the order of this reactant would be 0. So we'd say that overall, this reaction has a first order, and it's all dependent on the concentration of A. Changing the concentration of reactant B actually doesn't impact the rate.